Hi everybody, this is Tentralbeard, and on today's episode of How to Make Minecraft Shaders, we are going to learn some stuff for making clouds. And what we're going to do is we're going to go through a few different steps to get there. We're going to learn about adding extra composite shaders, so we don't just have our one full screen pass, but we'll do another full screen pass after it. Then we're going to learn how to use things like the sine waves we've done before, along with fract to make kind of random noise so that we can make a pattern out of seemingly nothing. And then we're going to use that staticky pattern and make it more curved and friendly and integrated, and we're going to make it kind of fractal. And we're going to go from a 1D noise like that to like a 2D noise that'll look like clouds by stacking a few layers together. And then after that, probably on another episode, we will start doing ray tracing, where we will take rays from our eyeball and we'll trace them through the sky to see where they hit clouds, and actually have like 3D clouds. But we're going to go through this step by step in a way that hopefully still explains it. It makes it make sense so that you actually understand the concepts and can then do your own thing with it. But we'll start at the beginning, which will be adding a composite pass, an extra composite pass. So let's get into that. So let's open up our Notepad. I'll note for myself there. Okay, so in our shader packs folder, let's take our old tutorial and we're going to copy paste so that we have good version control. You always want to do this when you're making stuff so you don't break things and not have a working version and have to go back to the beginning, because some of this stuff takes a long time to do. So tutorial 8, shaders. And first thing we're going to do is we're going to take our composite vertex shader. I'm going to copy it. And we're going to just paste it. I'm going to rename these. And this will just be composite 2. I want composite 2 and composite 2 vertex shader. And let's open up composite 2. And we're going to delete a lot of this because we want to just strip this down. We want to keep our settings. And keep frame time counter, sure. We don't need shadow stuff. We don't need G color. We'll call that color text 0. It's the same thing. If I spell it correctly, we want to keep our text chord. And here, let's see. For default, we want the color to load a texture 2D of the existing color at color text 0, because that's the output from our shader so far. Don't want to do anything with it. We just want to output it then back to draw buffer 0. And we'll save this. And let's go into Minecraft. And we will choose our new tutorial and apply it. Let's make sure the it's actually working by put our grayscale up. Okay, cool, it is working. Now to see if our composite 2 is actually working, let's change this color. We'll say color.rgb equals a vec3 of red. And let's see if that works. Get back to base, hit R to refresh. There we go. So we have a second composite pass that's working. Now we're going to do something to make it so that it works only when we want it to. We're going to create a setting. So let's open up our settings and let's open up shaders. In settings, let's make something called cloud style, let's say. Or just clouds. Yeah, let's do cloud style. We'll default it at 0 and we'll give it the options of 0 and 1 for now. We'll save this, and in our shader.properties, let's add an option to our front screen. So we'll use these little square brackets. Let's say clouds, to have a clouds menu, and we're to have a space between that and everything else. And then at the bottom, we will say screen.clouds, and this is spelled and capitalized the same. If I get rid of caps lock, and we'll have an option that would be our cloud style. Let me fix this up here too. save that as well. And we're going to add something actually to our shader.properties, which I've got just copy pasted here, so I would do it right and I have to look it up. Which is we're going to put one of our little define flags like we have in our other programs, that if cloud style is 0, we should disable composite2. So that's program.composite2.enabled equals false. That's how you do that. There's no semicolon, it's just text, because this isn't actually like GLSL, this is Optifine or Iris format. So let's, with all that saved, let's go back in here and refresh, and we see we're back without red, which seems that that composite is off. And let's go into our clouds menu, turn on cloud style 1, and it's on. Cool. So we now have the ability to turn composite 2 on and off. This is very handy because you want to have things not be automatically on in case they're performance heavy. We're also doing this in a second composite so that later on we can run this at a lower resolution, because ray tracing tends to be expensive. So often we will do it just for like a quarter of the screen and then enlarge it, because that's like 4 times less work. Okay, so let's get into a few different things on there. First thing we're going to do is we're going to make sure that we're only drawing our sky where there is sky, and then we're going to learn about randomness and noise and everything. So to do that, we're going to use another uniform sampler 2 here. So we'll just copy paste this, and we're going to take the depth text. Depth text 0 is probably the right one. And what we're going to do is we're going to sample that just like we sample the color here. If we want, we can go like this. Let's go down a line, copy paste it. Let's take a float and we'll call this depth, and it will be whatever's on our depth value here. And so that we can visualize it, let's put depth here and see if we can tell what that looks like. Let's save this and refresh it. It's probably just going to look white. I messed something up. Depth equals, oh, this only has one component, so we'll just take the X or the R. It's just taking that first thing. And this just looks white. If we go straight on the ground, you could see it. There's a little bit of gray. It does show things that are close as black and far away as white, but because most things, the way it's to save everything in a very wide space, it scrunches it down funny. So if we wanted to visualize it differently, we could say depth. Let's say it's a fract. We want to use fract today anyway. Depth times 100, let's say. And see what that does. What fract does is it gives you the fraction of something. So if you had like 1.5, it would just give you the 0.5. So when you want to visualize a very big number that goes beyond the 0 to 1 range that we visualize on the screen, you can use fract. And then here you can see like the distance. It's going, if you look at the floor, black is low and white is higher. So it's going from lower to higher as things get farther away from us. But it's doing that in steps. You can see that the first few steps are very small, and then each step is getting bigger, and that fourth step is pretty much as big as everything. And it saves things like that so that it can save all of the depth in a very small number. But we're going to use this value as a mask for our clouds, because anything that is at a depth of 1 is as far away as everything can be, so that will be our sky. So let's say that color RGB will be something else only if the depth is equal to 1. So if, and we'll do a little parentheses, depth is equal to 1.0, we're going to do something, and that's, we're going to open up these little curly brackets for what we're going to do. And if the depth is that, we're going to change our color to be red like we had before, just so that we know it's working. Let's make it blue, so that's 0 red, 0 green, and 1 blue. Let's get back in Minecraft, load this up, and there, we now have a mask for our sky, and where there should be sky, it's drawing blue. So that's good. We're in a step towards making our sky. So now we're going to make some learn about some randomness and stuff so we can make cloud patterns out of nowhere. There's different ways to make clouds using what we call noise, essentially static. It's kind of like a randomness. You can also load a texture, but if you load a texture, you still need to make it somewhere. So we're going to learn how to make one. So we're going to make our first function called random, and this is going to give us a pseudo-random number, and we're going to learn a way to do that. We're going to take in a vec2 that we'll just call p, that will be our 2D coordinates we're working off of. And what we're going to do is we're going to return a float. First, let's just return a sign. Remember, those are those waves we use for waving plants. It will say we'll take p.x and do a sign to it. And let's see what that does. It should give us a little wave, but we're visualizing it differently. Didn't look like it did anything. So let's say, what if we take x and we do, because x is just going 0 to 1, let's say we times it by 100 so that we can see this 100 times across the screen. Oh, we're not actually calling it anywhere, so it's not going to do anything anywhere. Let's say that our color would equal this random function, and this random function is going to grow. So the color RGB equals a vec3, and that vec3 is going to be made of our random function, which will take in not our text code, but let's say our UV. And our random function returns a float. Let's turn into that UV. So let's make that UV. Let's say that vec2 UV equals our text chord. And we'll do this times 100 here instead of doing it in here. Because we want to have whatever we're doing on the screen to do it like 100 times, or let's say 10 times, so we can actually see a pattern and not just, it doesn't make sense. Okay, so we can see now that we've got a wave that goes up and another wave that goes up. If you think the black is low and white is high, we've got a wave going up and then down, then up and then down. So we've just made a pattern. If we make our UV be a different multiplication of the text chord, like if it's 10 times or 100 times the text chord, then we should get this pattern 10 times more often. There we go. Because we're just repeating, we're sampling like a bigger area. So now let's do something else here. Let's say that we want to not just incorporate that. Let's look if we did the p.y. And this should be vertical lines if we did this. There we go. So that's kind of we're getting patterns. What if we did sine p.x plus p.y? What if we did both together? You'd think we'll get something like a checkerboard kind of grid pattern maybe. Oh, no, we've got a diagonal because it's doing this math based on that. So if we want to take something like this that's a wave and we want to get randomness to it, one of the easiest ways that a lot of people do that's really standard is we take this wave and let's say the wave is larger than 1. If this is 1 and this is 0, if we use fract, which gives us just those decimals between, like let's say if our number was 5.5, it would give us just the 0.5. It gives you that fraction. So if we have a wave that goes across multiple numbers and we take just the decimal, instead of looking like a curve, it's going to look like it goes like this. And then if we speed it up to a certain speed, it'll start looking like this random noise. So let's play with this some and see what we can get. So let's say that we want to get the fract of this. But we'll take this thing and we'll multiply it by, let's say 100, just so we have a very big wave getting chopped up. Let's go back in here. And look, now we've already got something that looks a lot more like static, like randomness, which is good because that's what we're trying to do is just get kind of like a randomness, just to kind of base something off of. It still has a lot of order, it looks like, to it. But if we did something like times this by some random number and times this by some random number, and we're going to have them be like this is 3 numbers and that's 2 numbers, so there's some kind of a magnitude difference. Let's look at that and see, then we're starting to get something that looks more kind of random. If we also wanted to throw time in there, we have our frame time counter. We could say let's also add in, let's see, plus frame time counter, and that's going to keep getting big. So we would take frame time counter, let's do a mod, which gives us kind of the leftovers of it divided by something instead of the leftovers of it divided by 1. So it's like fract, but a little bit different. Let's say 10, that would give us 10 variations, and then this should be static-y in time as well. There we go. So we've got static, randomness, and that's what we're going to use to start building our clouds. But instead of just having random things, what we're going to do is we're going to, well, for now, let's get rid of time because we want this to look very stable. We're going to make an interpolation between values so that we don't just have what looks like static. What we want to do is, if we're generating something very high here, which is white, and something very low here that's black, and something here that's gray, we don't want it to be these steps. We want it to kind of smoothly move between them. So we'll do that as a diagonal, and then we'll do that as a curve, and then we'll use that to kind of get cloud shapes. So we've got our random function. Let's also make now a smooth noise. And this will also take in a vec2 that we'll just call p. Let's make our little brackets. And what this is going to do is it's going to mix some of these numbers together. So if we were to sample on a map, let's say, let's make a new page here. So here's our map laying down on a table, and this point's really high, and this point's really low. If we wanted to, let's say this one's up here and this one's down here. If we wanted to draw this, we can kind of imagine in our head how this would work. Is that, you know, just like our vertexes are connected in the vertex shader, these corners would be connected, and that gives you kind of a 3D plane. And if we want to know how high this spot in the middle is, we could, but we only have these ones, we could do the same thing we did with varyings in the vertex shader. And we could say, well, it's going to be a mixture of where it is between these things. If this is here and this is here, then the spot between them will be between them in height. So if we take this corner and average them where the point is, and take this corner and average it where the point is, and then average between those two for how far between them this point is, we'll get how high this is. And since we're using black and white as kind of like a height or a density field, if we sample the corners, we can use the how far in between them this is to get it. So if this dot is right here, it's equal to this. If it's a quarter between these ones, it'll be a quarter of the values. And we're just going to interpolate between things to get something that makes more sense. So at the core of this, we're going to take in our thing, and we need to know a few things about it. So we want to know how far between the corners it is. So first we'll make our vec2 f, which we're using bad abbreviations. Let's use better abbreviations. No, we're not going to because I don't want to type them. So f will equal the fract, and just remember that, of p. And that'll give us how far between the corners it is in each direction. Because if it's halfway between 5 and 6, you want that 0.5, not the 5. We need a few other things. Let's see. So since we're doing a lot of mixing, we could do this as just one line even, probably, if we wanted to. So we want to mix between a few things. First, like I said, we're going to go between the top left and bottom right. We need to get all these values first, so let's create them. Let's say float a, which will be our top left, equals random, and we want to sample not where this point is, but where its corner is. So the top left, let's pretend that that's low numbers. So we want to take the lowest of the decimals, and floor gives us those. And then for B, you want to take the top right corner, let's say. So we want to take our vec2 where we transform. We want to bottom out the x, but not bottom out the y. So we'll take floor p dot x, and then ceiling I before e dot y. And ceiling takes the top of the value, so 0.5 would go to 1, here 0.5 would go to 0. We'll take the other corners here, so C would equal random vec2, and we're going to take ceiling. Hold on, 4p-x 0. I didn't do this the way that makes sense in my head. I'm imagining that the top left is zeros. So we're taking, imagining this is 0 and this is 1. For this, I don't know why I'm doing it, so let's say 0, 0, and we've got this one would be the high x and the low y. This one would be the low x. So my brain's having a moment. And high y. And then d will equal just high on both. So we're taking the lowest, then high on the right with not changing the y, and then low y but a high changed, or low on the x changing the y, and then change both. And then what we're going to do is we're going to mix together A and B. So we'll mix, it's another mix inside of a mix. We're going to mix A and B according to the f.x value. And we're going to mix that mix with mixing C and D by the f.x value. And we'll mix those two together by the f.y value. We'll take our smooth noise, and we're going to call that here where we call random, we'll call smooth noise. And let's go back in here, let's refresh. We're missing a parentheses somewhere. Let's make sure that our random still works, because apparently I broke that when I took out the time. Okay, our randomness still works. So make sure you got that with the right amount of parentheses. And then let's call that in our smooth noise function. And we'll call our smooth noise here instead of random. And let's see, I messed up a few things, it looks like. Oh, it's I before E except after C. Let's see that. And variable y. Let's see. Where do we have a y by itself? I probably, there we go. P.y. Okay, cool. So you see we've got randomness now, but it's kind of blurring between the things. If we change our scale here, let's lower that to 10, so we only get 10 iterations across the screen. You can see that it's blending between our things. So we've got those pointy hills now. They're kind of diamond-shaped static. If we want those to look even curvier and nice, there's a nice little trick we can do to kind of do similar to a sine wave. Let's add that in here, and we'll do it to just at the end, or at the beginning. We'll do it with our fract. Instead of fract, we'll smooth it. So let's make a smooth function, because this might not exist. We'll do, actually, let's see if it does first. Let's do smooth fract p, and let's see if there's a built-in smoothing function. There might be, there might not be. There is not. So let's make a smoothing function that smooths out of vec2. Say vec2 smooth. Take in vec2 b. Little brackets. And this is just a little bit of math. You can explore this on Desmos to see how this works. Okay, so we'll return v times 3 minus 2 times v. I think that does it. And this gives us like a kind of a curve, like a sine. If I did that right, let's see if I did that right. If I did, this will look more rounded. So apparently there is not a smooth function, but it doesn't want us to name this smooth. So we'll call this smooth on a v2. Call this smooth v2 because we're doing a smooth on a vec2. Let's see if that still works. It does. And you can see now this has like a nice curved roundedness to it as opposed to like a diamond pointed hills. And we're going to use this as the basis of our clouds. To make it look more like clouds, to start here, let's say that instead of our color equaling the smooth noise, let's say our color is plus equals smooth noise, and that means it's adding it. That's the same as saying equals color to RGB plus whatever is after the equal sign. This way we're just going to add the whiteness to our existing sky level. There we go. It doesn't look very cloud-like yet. So what we're going to do is we're going to make the smooth noise, so we're going to make a fractal noise that uses it. So it's like we used our random, or rather our random in smooth noise. We're going to use smooth noise in something else. So let's create float fractal noise. And again, we'll take in our vec2, just a point. And to do a fractal noise, what we're going to do is we're going to take, like with waves we did before, we got a big wave. And then if you stick a little wave on top of it, it kind of like goes like this on it. And you could stack multiple sine waves to get different things. We're going to do that with this. So we're going to need a few different things to do this. First, we're going to have our total. And we'll start that at 0. We're going to have our amplitude and frequency, just like the sine waves. We'll start those off at 1. And we're going to do a loop now. This is new for us. We haven't done a for loop yet, I don't think. What this does is it's going to let us do the same code multiple times. Kind of like a function is out of a thing. But the way we're going to make it work is we have to give it parameters for how often it should run. So if you just want to say like do something 10 times, you'd say for a counter of 0, like a counter of 1 to a counter until it reaches 10 and go up once each time. So we'll say for float, we'll just say I as a thing, put our semicolon, or a float I equals 0. We usually start at 0, it's just how you do things generally. We could start it at 1, and we'll say while I is less than iterations, and we'll say I plus plus. Plus plus means you're just adding 1 to it, and we actually need iterations to be a thing here. So we'll put that as a thing here we keep track of as well. Float iterations, and we'll have this be 4. We'll do this 4 times to start. So while our counter starts at 0, and while it's less than iterations, which is less than 4, we're going to count plus 1. So that should make this happen 4 times. What are we going to do 4 times? We're going to take our total, and we're going to add to it our smooth noise at point P. And then if we just did that, it would just add the same thing 4 times. That's no good. Let's make sure that at the end we return our total. So what we're going to do is for each wave, we're going to say that the amplitude times equals 0.5 is half as much, and our frequency times equals 2. So the waves will happen twice as often and be half as big. And to make those actually apply to this, we'll say we'll do it at p times frequency, and we'll take this whole wave times amplitude. And then we'll take our fractal noise, and let's make sure that we're using that where we're using our smooth noise. And if we refresh, we've got something going on here. It looks like it's a little bit too bright. So let's look at why that might be. Let's go to our picture. We're taking our first wave and we're adding our next wave to it, then we're adding another wave to it. So it just keeps going up. So let's say that we take our waves, instead of just adding 0 to 1, let's take half off of that. So it will be negative half and positive half, so that our wave won't just sit on top of the last wave, but going up and down from it. So let's say, over here, to smooth noise. So plus this, and then minus times amplitude. So let's make a thing here. Let's say it's 0.5. Oh no, wait, it's that minus 0.5. And maybe we should start our total at 0.5 then. Let's see what that looks like. There we go. So that kind of looks like clouds already, a little bit. But what we're going to do is to make it kind of have cloud movement, we're going to take 2 layers and move them over each other to kind of get like a cloud appearance. So we've got our UV here down in our main function. Let's get a second UV as well. And we're going to have this one scroll and be a different size. So let's get back our sense of time we have from frame time counter. This could be world time or anything else. And let's just add that in here. And we'll multiply it by a number, let's say 0.01 or 0.1. Let's see what that looks like. That might be way too fast, might be way too slow. Frame time counter is probably not something we want to use for that. Let's try world time instead, because then it will actually be tied to Minecraft time. Actually, frame time counter is probably fine, because then it'll run even if the game's paused. Let's see what this looks like. Nope, we want this to be UV2. And we're not doing anything with it yet. So what we're going to do is we're going to take our fractal noise here, and we're going to multiply it by a second fractal noise. That uses UV2. Let's see what that looks like. Okay, so now we have one of our clouds scrolling over the other one. And you see that makes it have kind of like those little patterns. Like there's something going on in the cloud, and it's kind of, they're appearing where there's the 2 overlap, and they're disappearing where the 2 don't overlap as much. But let's have it be a different scale as well. Let's have that be, instead of that, let's have it be 30 instead of 10, so that they will be 3 times smaller since it's sampling a 3 times bigger space. And now you see we've got our bigger clouds, and they have those small little patterns on the edges. But this is just it's not lined up to the screen, you can tell. It looks like our time is weird. Let's set our time. They're not really lined up to the world. They're not really kind of lined up in 3D. They're just kind of pasted in the background. But I think that's as far as we're going to take this first episode, just for the sake of time. And this gives us a few things we've learned. So what did we learn? We learned how to make another composite pass and have an option to turn it on and off. Let's check that still works. Yep, we could turn this off and on. So we learned about that. And in our new composite, we made a random function that gave us kind of like a staticky noise. We used a smooth function, which I didn't go into how that works, but you can just plug that into Desmos and see what it looks like. We made a smooth noise function by interpolating between the corners, like we drew in our thing. We took the 4 corner values and blended those values, get smooth noise, which used the smoothness to then have non-diagonal points, but rounded hills. And then our fractal noise called that same pattern and stacked it on top of itself in different amplitudes and frequencies, like we did with sine for our wavy leaves. And then in our main function, we were reading the depth texture, which we visualized, and then we were using our text chords at different scales. Have overlapping layers of our fractal noise, which move over each other to give us a little bit kind of like a cloudy look. And we'll work on these more to make them better in the next episode, to actually stick them as like a plane of infinite clouds that's 3D in the world. Maybe add some shading, and there's kind of like some fake kind of shading. And then after that, we'll get into ray tracing them as 3D clouds. I hope you all had a good time, and we'll do more next time.